Okay, so let's do a quick review. It's been a while since we looked at root locus, and so let's look at do a review. What we were looking for is a way to look at all possible solutions of the characteristic equation for a closed loop transfer function. The question is, can we find a quick and easy way to visualize how the open loop poles move through response to a changing gain? If we've got a simple system here with a gain and then a system, and we put a feedback loop on it, what happens when we change this gain and it goes from 0 to infinity? How does the response of the system change? Where do the closed loop poles move as we do this? Where are they going to end up in the S-plane? Because as we know, if we know where the closed loop poles are in the S-plane, then we know what kind of response to expect. So ultimately, we would like then to be able to not only know where they are, but then know how we can move them around to get the response that we want. And so if we start back here and look at the characteristic equation, and we're going to write it this way, in 1 plus GH, which is the characteristic equation. We know if we close the loop on this system here, we end up with G over 1 plus GH, and so the characteristic equation is 1 plus GH. If we set that equal to 0 and solve for the roots, and we do a little bit of manipulation. I showed you this before, so I'm not going to go through it in detail. But what we end up looking at and finding out is, in the case where k is equal to 0, our gain is turned all the way down, k is equal to 0, then the closed loop poles are equal to the open loop poles. Okay, so our closed loop poles are going to lie where our open loop poles are. Remember, we're looking for a quick and easy way. So if we know where the open loop poles are, and the open loop poles usually are pretty easy to get to, or they are in a lot of times, we can find the closed loop poles when k is equal to 0. Now, the next case, case 2, is when k is equal to infinity. In this case, we do a little bit of manipulation there, and what we find are that the closed loop poles are equal to the open loop zeros or infinity. And so we find out that what we're going to conclude from that, we can conclude that the root locus branches start at the open loop poles and end at the open loop zeros. Okay, so that's an important distinction that you need to make. We're going to start at the open loop poles and end at the open loop zeros. And in that, we're going to capture all possible solutions for the closed loop poles. It's going to show us, as we turn the gain from 0 to infinity, what's going to happen as we move that. We show those closed loop poles moving around on the S-plane, showing us different types of responses. Okay, so that's the basic that we're going through here. Now, back in the mid-1900s, this was a thing. People were trying to figure out how to do controls, and this was a task that they were looking at. And they came up with this method of sketching these root locus. Okay, so that's what we're going to look at here. Now, we're very fortunate in that we have MATLAB, and that if we want a real detailed root locus, we can just simply ask MATLAB to give it to us, and it will. And the command for that is rlocus, and the transfer function that we're interested in, and it'll show us the root locus for that transfer function. Now, that's good and well and good, and we like that, but it doesn't help us with design. Design happens in your head, and you need to know where these. You need to see in your mind where these root locus are going to go. And so these are the rules that technical rules that we have to draw them. Now there's more rules in here that I don't include, but these are the rules, and we're actually going to use down through about here. We're only going to use a couple of these rules, and with that we're going to sketch this root locus. If you wanted any more detail, again, you can go to MATLAB and get it in great detail, but we're just going to use a few of these rules. We're going to take the closed loop transfer system, transfer function. We're going to divide it, or going to separate it into first and second order systems, so we can find the poles and the zeros for it. We're going to find out how many branches go to infinity, and by looking at the difference between the number of the poles and the number of zeros. And so we'll know how many are going to infinity. Then we're going to look at where the asymptotes of those branches that are going to infinity, where those intersect the real axis, which is this equation, the sum of the poles minus the sum of the zeros divided by the number of the poles minus the number of zeros. And then we look at the angles, and this looks really complicated in here, the angle of the asymptotes, but it's not actually as hard as it sounds. If we have one branch going to infinity, it's going to go at 180. If we have two branches going to infinity, it's going to go plus and minus 90. If we have three branches going to infinity, one of them is going to go to 180, one of them is going to go to plus 60, and one of them is going to go to minus 60. And then if we have four of them, we're going to have them going at plus and minus 45 degrees in here like this. And so we probably won't get much beyond that, but if you need to, you can go through and calculate where all these branches are going to go. Now these are the asymptotic lines. Then we're going to plot the poles and zeros, and we're going to find out where it is where the root locus lies along the real axis, and from that, then we're going to sketch this. Okay, and it sounds a little bit harder than it is. Actually, once you get the hang of it, it's really, really easy. So I'm going to stop here, and then we're going to do some examples.